Okay, so let's say you've got these two molecules and they're interacting with each other using the usual Leonard-Jones potential energy graph. Like let's say you have just the graph we were looking at last time with an energy axis and a distance axis. So the usual energy and distance are just being distance between molecules. We can use the general shape we were looking at last time of something like this. So that's our usual potential energy shape that we expect for just a pair of neutrally charged molecules interacting with each other. And based on that, and usually just for the notation, we usually call that lowest energy that it reaches negative epsilon. Negative epsilon. Negative 1 epsilon. And that lowest potential energy occurs at, what's our usual expectation for that distance, where we expect lowest possible energy? Yeah, 1.12, specifically 1.12 sigma, where sigma is the diameter of the particle. And we usually call that distance R naught. So R naught is about 1.12 sigma. So there's our potential energy graph. And what information would we need to know to figure out whether these molecules are bonded to each other or unbonded?
Does it have to do with the distance?
To some extent, the distance. But the thing is, it's possible to be a certain distance apart and bonded, or to be that same distance apart and unbonded. So it's not just about distance. Yeah, you're going to need to know something about the E total as well. If you know E total, like let's say E total happens to be negative 1/2 epsilon. I'll just draw that as a green horizontal line here. And why would we expect E total to be a horizontal line?
Total is not changing because it has to be the sum of your potential and kinetic added together.
Right. We're assuming that, yeah, E total is the total amount of energy in the system, potential and kinetic energies together. And since we're assuming this pair of particles is a closed system, they're interacting with each other, but nothing else, we can assume that total energy does not change. Therefore, it should be a constant, so its graph will look like a horizontal line. And from that horizontal line, assuming we know E total, let's just say we happen to know that E total is negative 1/2 epsilon. How would we draw out the kinetic energy graph there? What locations can we immediately put on the kinetic energy graph?
One thing I've seen many people do, and I would do this in my F&T, was we would take the area that's beneath the E total line, and we would just kind of flip it on top for the positive coordinates.
And why is that? Why can't we just take the potential energy graph and flip it? Why would that produce the kinetic energy graph?
I'm not too sure.
If we go back to the idea that E total is the potential energy and the kinetic energy added together, we know the value of E total. We have a formula for potential energy, or not necessarily a formula, but at least a shape of the graph. If we want to know kinetic energy, how would you solve for kinetic energy here, just algebraically? How would you isolate kinetic energy in that equation?
It would be E total minus the potential energy.
Right, E total minus the potential energy. Regarding minimum kinetic energy and maximum potential energy, the problem is potential energy doesn't have a maximum. Potential energy graph just keeps going up and up and up forever here. So there isn't really a maximum potential energy. But they are related in this fashion here, that the kinetic energy is always going to be the total energy minus the potential energy. And yeah, we could, for instance, just fill in some values. We know when potential energy is a certain value, kinetic energy is going to be E total minus that value. So for example, at that lowest potential energy, we know that the potential energy at R naught is -1 epsilon. If you fill that in, kinetic energy at R naught, that'll be E total, -0.5 epsilon, minus potential energy, which is -1 epsilon at that location. So yeah, add those or subtract those, we get +0.5. So we at least know at that location, at R naught. And yeah, also we know kinetic energy cannot be negative. So if we get any value of kinetic energy that's a negative value, we know that doesn't actually happen. That is, if there's a certain location that suggests at this location kinetic energy is negative, that means that the particles can never actually be that distance apart. We do definitely know that we can mark -0.5 epsilon, sorry, +0.5 epsilon when the distance is R naught. So let me put that on the graph. You know that at R naught, the kinetic energy is +0.5 epsilon. So that's 1 point on the graph. Also, is there any location where we know that the kinetic energy is 0? Because we know it's never going to be negative. Can we establish a boundary by figuring out where it hits 0? Like, what has to be true to make kinetic energy 0 here? Yeah, when potential energy and E total equal each other, yeah, in this case, -0.5 epsilon, E total minus itself would be 0. So if we look for any locations on the graph where potential energy matches E total, those will be the locations where the kinetic energy is 0. So in this case, that looks like it'll be here and here. We've got 2 locations where E total matches potential energy. So tracing those up to the axis, we could mark this R value and this R value. At those 2 R values, which we usually call R min and R max, the smallest R can be and the largest R can be, we know that at those locations, kinetic energy has to be 0 because potential energy is E total. And then for the in-between values, we can use the idea that, again, kinetic energy is the difference between E total and potential energy. So for instance, let's say we start at R min, the far left point here. Kinetic energy is 0. If we go to the right from there, what happens to potential energy? That should probably be a little higher. Yeah. What happens to potential energy as we go to the left from R min? Yeah, potential energy is decreasing. Well, specifically from R min, from this location right here. As we go to the right, did I say to the left? To the right. As we go to the right, potential energy is decreasing. And if potential energy decreases, what else has to happen to kinetic energy? Yeah, we should expect kinetic energy to increase at the same rate that potential energy decreases, because those have to add up to the same constant E total. So an increase in one has to be matched by a decrease in the other. Continuing to the right, potential energy levels off to a minimum. So kinetic energy is going to level off to a maximum. Then potential energy increases slowly, then quickly. So kinetic energy has to decrease slowly, then quickly. So our kinetic energy graph is going to look something like this. We can also get that algebraically, going back to the idea that the potential energy graph and kinetic energy graph are just mirror images of each other. The reason for that, if we go back to the idea that kinetic energy is E total minus potential energy, or if you rearrange that a bit, kinetic energy is negative PE plus E total. If we think of this as kinetic energy is negative potential energy plus E total, potential energy is this graph. What happens to a graph if you apply a negative sign to the function? Yeah, it's going to reflect it. So if we take the entire potential energy graph, let's say we just take the entire graph and flip it over. So the entire potential energy graph if we just apply a negative sign, all that's going to do is flip it across the axis. So it'll look like this instead. So this light blue curve here is negative potential energy, but then we're also adding E total. What happens when you add a constant to a function? What would that do to the graph? Yeah, that's going to shift it up or down. And specifically, since we're adding E total is negative value, so when we add a negative, that's going to shift it down. So this curve, this light blue curve, flipped and shifted, is going to be our graph of negative PE plus E total. However, if we want this to be a kinetic energy graph, what are the only values kinetic energy can have? Or what values can't be for kinetic energy? Yeah, kinetic energy can't be negative. It can only be positive or zero. So that means we should ignore everything under the axis and just look at the region above the axis. So there's our kinetic energy graph. It's exactly the potential energy graph flipped over across the axis and shifted. And then we ignore everything below the axis, and that's our kinetic energy graph. Any questions on the algebra or graph theory behind all that?
So after like the kinetic energy hits zero, but the potential energy is still changing, does that mean the kinetic energy is just at zero after that point? Like if you go to the right of like the red curve?
Well, if we do go further to the right here, we'd end up with mathematically kinetic energy would have to be negative. But kinetic energy can't be negative. So that means that this region doesn't even exist. It's impossible. So what that tells us is not that, it doesn't tell us beyond that point kinetic energy be zero. It tells us beyond that point is impossible. In other words, the particles cannot be further apart than R max. And likewise, the particles cannot be closer together than R min. So we would just say this region and this region are forbidden zones. The particles cannot exist this far apart, cannot exist this close together. They can only be in this narrow range. Yeah, exactly. This would be described as a bounded state, or the particles would be bonded together. And bounded, and mathematically bounded or bound just means that there's a finite region of space where it can exist. It can only exist between R equals R min and R equals R max. They can't be closer together than R min. They can't be further apart than R max. So there's a finite region of space where they can exist. Whereas unbounded would be if there's either no R min or no R max, if it can just keep going out to infinity. But that's not the case in this situation. Any questions on that so far, or any other questions? Also, how would you describe the behavior of these particles? They're definitely bounded, but what are they doing? How would you describe their motion? If they can get as close to each other as R min and as far apart as from each other as R max, what are they doing in between those?
They're interacting because if you put your finger on the graph and go towards the right part of the potential energy where the graph starts approaching zero, then at that point the two particles are so distant to the point where the force between them is so weak. So
if they were getting that far apart, but remember they can't get that far apart here.
Yeah.
The only region they're allowed to be in at all is this region.
Okay.
So within that region, and of course, if we had more energy, then it would allow them to get further apart. But with this much energy, they can only exist between R min and R max for that energy level. At R min and R max, they're briefly at rest. But let's say they're so far apart, they're at R max. They've come to a stop, but at that point on the graph, can you tell from the potential energy graph which direction the force is going to be?
To the left, because force is the negative slope of potential energy.
Exactly. We have, at this location, we've got a positive slope. So that means the force is going to be in the negative direction. And in this case, the negative direction doesn't so much mean to the left, it means in the inwards direction. That is, the particles are attracting each other, acting to decrease the distance. So if the particles are as far apart as they can get and at rest, there's a force causing them to attract each other. So they're going to start sliding inwards towards each other. And note that as R decreases, kinetic energy is getting higher and higher. So the particles are getting faster and faster and faster. They get to their fastest as they hit equilibrium, and then they keep going. So they start off at rest, they get faster and faster and faster. After they pass equilibrium, though, what happens?
They would repel each other?
Yeah, from that point onwards, after they pass equilibrium, they're too close, so they're repelling each other. They're still traveling towards each other, but they get slower and slower and slower, come to a stop when they reach R min, and then they're still repelling, so they bounce back out. At R min, they come to a stop, bounce back away from each other, get faster and faster and faster as they go through equilibrium, and then again, slower and slower and slower, gradually come to a stop at R max, and then repeat the process because they're back where they started. So overall, they're just oscillating. They come to a stop at R max, bounce back or rebound back in, get faster and faster, slower and slower, come to a stop at R min, bounce back out, faster and faster, slower and slower. So they're oscillating back and forth between R min and R max, with the fastest speed happening as they pass through equilibrium. That's what a bounded state for this pair of molecules looks like. It's oscillations between a closest distance and a furthest distance that are allowed at that energy level. Any questions on that so far? So if we try raising the energy, because remember this kinetic energy graph is because we chose this specific E total. If we try, let's say we raise the total energy. If we increase E total here, let's say we raise E total up to almost up to 0. By raising E total, let's say to negative 0.1 epsilon. Now what's the highest kinetic energy going to be? What would be the maximum kinetic energy here? Yeah, it should be 0.9. If we go back to the idea that when the total energy is negative 0.1 epsilon, then the difference between that total energy and the lowest potential energy, negative 1 epsilon, would be positive 0.9 epsilon when we subtract those. So the highest kinetic energy is going to be positive 0.9 epsilon. So that'll be somewhere more up here. And also, if we go back to the idea of thinking of this in terms of taking the potential energy graph, flipping it over and shifting it, now we're going to shift this higher. And note that the asymptote should still be E total, should still be approaching E total. So something like that. And that means, do we still have an R min and an R max here? If we go back to the idea of finding kinetic energy, finding locations where kinetic energy is 0 by looking for those intersections, do we still have locations where E total equals potential energy? Does E total intersect the potential energy graph anywhere? don't we still have some intersections? Like, looks like right here, potential energy matches E total. And also over here, it looks like there's another match. So it looks like there are a couple of locations still where potential energy meets E total. Anywhere where those graphs intersect, that means the potential energy value and the E total value at that location are the same. And if E total is equal to potential energy, there's nothing left for kinetic energy. So we still have an R min and an R max. They're just at different locations. Like here's our new location for R min. And yeah, it looks like the E total being negative is what's causing this. That as long as E total is negative, then there's still going to be some location where E total hits potential energy. So at those two locations, we still have an R min and an R max. And notice that R min has shifted a little bit closer in. R max has shifted a lot further out. So our kinetic energy graph is still going to look like the potential energy graph flipped upside down, shifted and cut off at 0. It's just that now there's a lot more of it. So this would be our new kinetic energy graph at the higher total energy level. And notice that this is a very different shape than what we had earlier. We would still consider this to be bonded because the particles, there's a closest they can get and a furthest they can get. They're occupying only a finite range of possible spaces. But some things have changed. If we compare this to the previous kinetic energy graph, previously it looked like this. Previously, the kinetic energy graph was pretty close to a parabola. Not exactly a parabola, but pretty close. And what other physical situation also leads to the kinetic energy graph being this upside down parabola? Where else have you seen a kinetic energy graph that looks like that upside down parabola? Or to put it another way, what other type of potential energy leads to this sort of shape for kinetic energy? Yeah, a spring. If you're dealing with a spring, the spring potential energy graph is an upwards opening parabola. So the kinetic energy associated with that spring will be a downwards opening parabola. And of course, these molecules are not connected by a spring, but the kinetic energy graph being shaped like that upside down parabola means they'll behave like they're connected by a tiny invisible spring. If we raise the total energy though, notice that this new kinetic energy graph doesn't really resemble a parabola. It's not symmetric for one thing. It gets steeper and steeper on the left side and less steep on the right side. So this is no longer going to act as much like a spring. It's still going to be oscillating, but it's oscillating asymmetrically. On the inner side, as they're getting closer and closer, they approach Rmax really quickly and bounce right off because it's very steep here. That represents a very rapid change in speed. But further out, they've got lower kinetic energy. So they're drifting much more slowly out to Rmax, come to a stop, and then much more slowly drift back in, and then bounce rapidly off of R min. So where are they spending most of their time? If these particles are higher energy, which region are they spending most of their time in? Closer in, further out, near equilibrium? What do you think? Yeah, they're spending most of their time further out because they're traveling slowly in that region. So they're spending a lot of time far apart from each other and then come back in and bounce off each other real quick, but they're spending most of their time traveling slowly further out. So that's what's happening at higher energies, which means the particles are going to be on average further apart from each other, which is why when you heat up an object, it tends to expand a little bit. The particles are able to spend more time further apart from each other. So that would be still bonded, but bonded at a higher energy level. Any questions on that so far? So if we raise the energy even more, how high would we have to raise the energy to make it unbonded, to get rid of the restrictions on location? Yeah, if we raise E total all the way up to zero epsilon, let's say we make E total exactly 0. In that case, we'd be raising this even higher. And at this point, we now drawing the kinetic energy curve. There's still an R min. There's still a location where potential energy and E total intersect. So that's the closest they can be. But if we look further to the right, where does E total hit potential energy again? If we keep going further out, yeah, it doesn't hit it at all. There is no R max because E total being 0, if E total is 0, that means that it is the asymptote for potential energy. So potential energy is never going to hit E total at this point. That means there is no R max, and our kinetic energy graph is going to look something like this. It still has, let me put this in a different shade of red. It still has an R min. It still hits a maximum kinetic energy, which would now be positive 1 epsilon. And it still decays towards an asymptote, but since it never reaches 0, kinetic energy graph is going to keep going. So these particles are now unbonded. They can just keep drifting further and further out. They'll get slower and slower, but they never actually come to a stop. There's no furthest distance they can reach. So this would be unbonded. 0 total energy is the boundary between bonded versus unbonded. Anything less than 0 and the particles are bonded. Anything 0 or more and there's no R max, so the particles are unbonded. Then if you raise E total even higher, you're just going to get an even higher kinetic energy graph. So it would end up looking something like this. That doesn't make it more unbonded. Once you've broken the bond, it's no longer bonded. But that higher kinetic energy means it's now able to move faster. So not only do they keep going outwards at a pretty fast speed. Any questions on those different kinetic energy graphs and those different behaviors? So let's see if we can translate this to the idea of bond energy. If you want to break a bond, how much energy do you have to add to this one pair of particles to guarantee that you've broken the bond? You got to bring the energy up to, well, first of all, what's the lowest the energy could possibly, yeah, you got to bring it up to 0 or higher. But where could it have started? What's the lowest, like worst case scenario, what's the lowest energy this could have started with? Yeah, the well depth. It's possible that the particles could have been all the way down at E total equals negative epsilon. So that would be the lowest possible energy state. If you want to guarantee that you're breaking a bond, you have to add enough to take it all the way from the lowest energy state, negative epsilon, up to 0. In other words, you've got to add plus epsilon. So this is a very useful way of thinking of epsilon. Epsilon is the energy you must add to guarantee breaking one bond. That is, separating a single pair of particles. And this translates really nicely to the idea of bond energy. You want to break one bond, you have to add epsilon. If you want to break 10 bonds, you have to add 10 epsilon, and so on. If you can figure out how many bonds there are in a system, you can just multiply that by epsilon, and that'll tell you how much energy you need to add to break all the bonds. Any questions on that so far? Yeah, I think this is probably one of the best ways to think about epsilon. Epsilon is the energy you have to add to guarantee breaking one bond, one pair of particles. So let's try applying this to a system with more than just 2 particles. Let me clear out some space here. I think we don't need the kinetic energy graphs anymore. We can look at just potential energy. And yeah, bond energy, if we want to find the bond energy of a cluster, like let's say we've got a cluster of maybe let's say we have 6 particles arranged in sort of a rectangular grid. Six particles, all identical, arranged in this rectangular grid. And let me label these just so we can get an idea of how we're going to talk about them. Let's say these are just labeled A, B, C, D, E, and F. If we want to keep track of all the bonds here, what would be some bonds, some examples of bonds that have that are at that equilibrium distance from each other? Like, what would be an example of a pair of bonds where you'd say the energy of this bond is epsilon? Yeah, AB, for instance. The bond from A to B is, that's presumably equilibrium distance. If A and B are right next to each other, if they're too close, they're going to repel. If they're too far, they're going to attract. But presumably, maybe they're oscillating, but on average, they're equilibrium distance apart from each other. So we can say that the bond energy of that, technically the bond energy would be negative epsilon. Positive epsilon is the energy you have to add to break the bond. So that's another thing we should consider here. The energy of one bond is negative epsilon. Negative epsilon in the sense that we define the energy of a bond as less than 0. To break the bond, you have to add energy to bring it up to 0. But this is an important thing to consider. Any bond has a negative amount of energy. Creating a bond requires removing energy to create that negative amount. Destroying a bond requires adding energy to bring that negative up to 0. So this is why, I mean, at the beginning of the quarter, it may have been somewhat confusing, the idea that you have to add energy to destroy bonds and remove energy to create bonds. The reason for that is a bond has a negative amount of energy. So you've got to add energy to cancel it out or remove energy to create it. But each one of these bonds, like AB, for instance, has an energy equal to negative epsilon. But the energy you'd have to add to break the bond would be positive epsilon, to bring it from negative epsilon up to 0. And yeah, we also have, if we just tally all these up, we've got AB, BC, DE, EF, AD, BE, CF. So it looks like that's what, 7? We have 7, and we would usually call these the nearest neighbor bonds. 7 nearest neighbor bonds. And each one of those has an energy of negative epsilon. So each one of those is negative epsilon. We've got 7 copies of it. So what's the bond energy of all 7 of those bonds? Yeah, negative 7 epsilon. So negative 7 epsilon would be the energy of all those nearest neighbor bonds. However, those aren't the only bonds involved, because A, for instance, could also be interacting with what other atom other than just B and D? Yeah, A interacts with C or E or F. So we should consider, if we want to be really accurate, we should consider all the bonds. For example, if we consider the bond from, let's say, first of all, which other than B and D, which atom is next closest to A? Yeah, E is next closest. And if you're not sure, you can always think of this as sort of an expanding circle. If you imagine you've got a circle expanding outwards from A, as that circle expands, the very next atoms it hits are B and D. So B and D are the closest, the nearest neighbors. But if you expand it further, the next atom it hits, and we really care about hitting the center of the atom, the next center it hits is E. So E would be the second nearest neighbor. If we keep expanding, eventually we're going to hit the center of atom C. So C would be called the third nearest neighbor. And then expanding further, we eventually hit F. So F would be the fourth nearest neighbor. If you imagine this expanding circle, or in 3D, an expanding sphere, that's a good way of thinking of where, or figuring out what's the nearest neighbor, the second nearest neighbor, the third nearest neighbor. It's just whichever one, the order they're hit by this expanding spherical shell. But let's take a look at that second nearest neighbor, A to E. What's the distance involved there? Or how would we find that diagonal distance? Yeah, Pythagorean theorem should work well here. If we have, well, it's Greek anyway, so it doesn't really matter how you spell it as long as it's recognizable. So let's say you've got atoms A, well, that would be D, I guess, A, D, and E. A, D, and E, and we can set up this is a right triangle here. We know, what are we calling the distance from A to D and the distance from D to E? Epsilon would be the energy, but if we're talking about the geometry involved here, we need to be working with distances. So what do we call the distance from A to D or from D to E?
It would be R naught because it's at the equilibrium distance.
Yeah, generally we assume that any nearest neighbor particles are equilibrium distance apart from each other. So that's going to be R sub 0 and another copy of R sub 0. You could also write that as 1.12 sigma, but it's usually easier to work it out in terms of R naught. And then if you need to, substitute 1.12 sigma in the final answer. And we want to know this diagonal distance. So if you set up the Pythagorean theorem here, leg squared plus leg squared equals hypotenuse squared, what's that hypotenuse going to equal? How does that relate to R naught? If we've got leg squared plus leg squared equals hypotenuse squared. When you solve for H, what are you going to get there? First of all, to simplify that, yeah, we can start by combining these to 2 R naught squared. So we get 2 times R naught squared equals H squared, because you can combine like terms there. But then what else do we still need to do to isolate H? Yeah, take the square root of both sides. So H is the square root of 2 times R naught squared. And square roots distribute across addition and, distribute across multiplication and division. Square roots do not distribute over addition and subtraction, but they do distribute over multiplication and division. So we can split that up into square root of 2 times square root of R naught squared. Square root of R naught squared is just R naught. So we get square root of 2 times R naught. Square root of 2 is about 1.414. So that'll be this diagonal distance, 1.414 R naught. And what we can do with that, ultimately the reason of why we want this distance in the first place, we'd like to know what's the energy of this AE bond. We know the distance. How can we translate a distance into an energy? What tool do we already have on screen right now that tells us how distance and energy are related? Yeah, we've got this potential energy graph. We've got R naught as the equilibrium value. And we could mark this off in units of R naught. Let's try that at first. Let's say we got R naught, and then twice that far would be 2 R naught. And then a little to the left of the halfway point would be 1.4 R naught. So let's say something like this. A little further to the right would be 1.414 R naught. Square root of 2 R naught. So based on that, that location, and ideally we'd want a more accurate graph than this. This one's just a rough sketch. But based on this 2 R naught here, we can trace that down to the graph itself, and then over to the energy axis. And this value should tell us the energy of that bond. And just as a rough estimate, this looks like maybe a fifth of the way from 0 to -1 epsilon. So I'm going to guess that's about -0.2 epsilon. Just as a rough estimate, ideally you'd want to use a more accurate graph than this with finer grid lines and more labels. But it looks like that's about -0.2 epsilon. So to keep track of these second nearest neighbor bonds, it looks like that's about -0.2 epsilon each. For instance, the bond from A to E. But how many other bonds do we have that are like that? What other bonds are that same distance? That same diagonal. Yeah, from B to F is that same diagonal. Any others? C to E. And yeah, B to D. Looks like that's all of them. Those are all those immediate diagonal bonds. So it looks like there's 4 copies of that. 4 second nearest neighbor bonds at an energy of -0.2 epsilon each. Then we can multiply those. Number of bonds of that type times energy of each of those bonds. We get -0.8 epsilon. So that's the energy contribution of just those second nearest neighbor bonds. And by the way, how does that compare to the energy from all the nearest neighbor bonds? How does that -0.8 epsilon compare to the -7 epsilon we already established? Yeah, that's a pretty small fraction, a very small amount. Looks like maybe 11%-ish. So the energy contribution from the second nearest neighbor bonds is very small compared to the energy contribution from the nearest neighbor bonds, which means if we had just ignored the second nearest neighbor bonds entirely, if we had looked at just the nearest neighbor bonds, we wouldn't really be all that accurate, but we'd be pretty close. -7 epsilon is a pretty good estimate for the bond energy of this cluster. -7.8 epsilon, combining these together, would be a much better estimate though. So using just the nearest and second nearest neighbor bonds, we could say Ebond is about -7.8 epsilon. In other words, you'd have to add 7.8 epsilon to this system to break all the bonds. However, if we want to be really accurate, what other bonds should we also include? Is A bonded to anything else we haven't counted yet? What would be the next further distance? Yeah, let's say the third nearest neighbor bonds. I mean, yeah, sometimes they call them next to nearest neighbor bonds. I usually find it easier to just refer them to nearest, second nearest, third nearest, fourth nearest, and so on. A to F, we can actually go a little closer than A to F. What's slightly closer to A than F is? Yeah, A to C is a little bit closer. Specifically, what's the A to C distance? How far is it from A to C? Remember, the distance from A to B is R naught. So from A to C would be how far? Yeah, 2 R naught. So we take a look at the graph again. From 2 R naught, trace down and figure out what's the energy there. Maybe -1.5 or -0.15 epsilon And again, you'd want a more accurate graph to be really good with this. But it looks like we have two copies of that because we've got A to C and also D to F. So we would list out two copies of the third nearest bonds. And let's say that's about negative 0.15 epsilon each. Multiply those. 2 times negative 0.15 is negative 0.3 epsilon. So that's another tiny contribution. How do we know it's 2 R naught? Well, we already know that the distance from A to B is 1 R naught, and the distance from B to C is 1 R naught. So since that's all along a straight line, we can just add those up. R naught plus R naught is 2 R naught. We don't even need to use Pythagorean theorem here because it's all one-dimensional. It's just one straight line. And note that that's the negative 0.3 epsilon, that's an even smaller contribution. It does make a correction to what we have so far. If we add all these up, instead of negative 7.8, we get negative 8.1 epsilon. So this would be more accurate. And then we could go even further. We could add in the fourth nearest neighbor bonds, which would be, for example, the long diagonals from A to F and from D to C. So for that, you would use the Pythagorean theorem again, using one side that's R naught and one side that's 2 R naught, and then calculate the diagonal. I think that'll be square root of 5 R naught, which will be even further out and therefore even weaker bond. So that's going to add an even smaller contribution to the bond energy, making a slight correction, but negative 8.1 epsilon is going to be a pretty close estimate because the further and further you get, the less contribution it makes to the bond energy. But if you want the exact bond energy, you should be including all the bonds. If you just need a pretty good approximation, you can probably stop after the nearest and maybe second nearest neighbor bonds. In fact, for very large clusters, we often just consider the nearest neighbor bonds and that's it. Because throwing in the second nearest neighbor bonds adds a lot of extra calculation, but doesn't really change the result very much. The nearest neighbor bonds is a pretty good estimate for very little calculation involved. But this is a general idea. You want to figure out how many bonds of this type are there, multiply that by the energy of one bond of that type, which is going to be either negative epsilon for the nearest neighbor bonds or negative some fraction of epsilon for the further bonds using geometry in the graph. Add those all up and you get the total bond energy of that entire cluster. Any other questions on that? All right, try applying these ideas to practice problems on your own. Let me know if you have any questions and we can look at some more examples next time. See you then.